Okay, so before we proceed further, I would like to share with you one videos that is probably it can help you to refresh what we have learned in the previous class. Okay. Oops. I think I need to make a new share. Or can stop share because I need to ensure that the sound is there. Okay. I hope you can hear the sound.
For fishing purposes only. Please at home and oceans clean. If you were to let a helium balloon go on a calm day, it would float up. The flight path it would take would be straight up. On a windy day, however, the balloon would drift with the wind and follow a flight path that is angled compared to the ground. When an aeroplane takes off on a calm day, the angle between its flight path and the ground is called the angle of climb. Just like the balloon that drifted with the wind, when an aeroplane takes off into the wind, its angle of climb is steeper and the ground roll is shorter. Taking off into wind is particularly useful to aeroplanes, as it helps them avoid obstacles such as trees on the ground. The reason the ground roll is shorter is that when the aeroplane is taking off into the wind, its takeoff ground speed is lower. For example, both aeroplanes will take off at the same airspeed. Let's assume it's 60 knots. The aeroplane taking off in nil wind will have a takeoff ground speed of 60 knots. But the aeroplane taking off into a 20-knot headwind will have a takeoff ground speed of 40 knots.
Here you can see if there is no wind, no headwind, no tailwind, so the takeoff speed is 60 knot. But when you have a headwind of 20 knots, then the ground speed of the aircraft is only 40 knots because 40 plus 20. The same goes if you have a tailwind. If you have a tailwind during takeoff, then the aircraft need to go much faster lah. Okay, because we are talking about the relative speed of the aircraft to the ground. Okay.
Both aeroplanes will reach the same altitude in the same amount of time. Altitude gained with respect to time is called the rate of climb. For example, if both aeroplanes will reach 1,000 feet in 2 minutes, their rate of climb is 500 feet per minute.
Okay, I think that's pretty much what we have learned last class. So for this class and the next class, I think we will look into the what we call accelerated flight. Okay, turn performance. So we will look into 3 items, basically the level turn flight, pull up and pull down maneuvers, and the flight envelope. This is very important. The things on the right hand side here, this is what we call it the VN diagram. Okay, I will explain on this part on the next class, okay, for this VN diagram. But for today, we will try to cover level turn flight. Okay, so level turn flight means level during the aircraft turning to the left or to the right, the altitude is not changing. Okay, the altitude is remain the same. The aircraft is maintaining its original altitude. That is what it means by level. Okay, level turn flight. So the aircraft is turning, okay, to the left, for example, but it will stay at the same altitude. Understand? Okay, this is the top view. Don't because if you look in a glance, or you just look at it without really read this part, top view, I think it seems like this aircraft is climbing. No, this aircraft is actually just turning. You look at it from the top. Okay. So our study of static performance, no acceleration, in the previous class, or in this book, we call it in chapter 5. Basically, we look into how fast it can fly, how far it can go, etc. Right? However, there are more questions to be asked: how fast the aircraft can turn, how high it can basically zoom or can go, what ground distance are covered during takeoff and landing. The answer to this question involve accelerated flight, okay, accelerated or decelerated flight later on. For accelerated for takeoff and decelerated for landing later on. Okay, the flight path and forces for an airplane in a level turn is given here in figure 6.1 on the left hand side here. The flight path is curved. Okay, the flight path is a curve, or in this case, it is like a circle. This is different to what we have learned before. Even though last class, we are talking about a climbing flight, but for that climbing flight, we are talking about the climbing in a straight line, in a linear. It is linear, okay? The climbing in a straight flight path. But in this case, we are looking into the curved flight path. Okay. And during this flight, we can see that the airplane is on this front view. The airplane is banked through the roll angle of psi. This one, psi of phi. I think phi. It is what called by this particular symbol, PHI, if I'm not mistaken. Okay, the magnitude of the lift L and the value of this bank angle are adjusted such that the vertical component of lift denoted by L cosine phi. Okay, this is phi actually. F, you need to this is actually this symbol is exactly equals to the weight. So in this case, the vertical component of this lift force. Okay. So L cosine phi is equal to W. Okay. So this must equal to W. Otherwise, your aircraft will slowly going down, right? Okay. If this component is higher than W, what happens is your aircraft is going up. Okay. So if you notice from this part, L is actually bigger than W. Okay. L is bigger than W because L cosine of this particular angle is equal to W. Cosine of phi, the value of cosine phi, I presume it is less than 1. Okay, you need to multiply by L. So in this case, L must be larger than W. Okay, later on we will look into example. And in this particular example, so you can see there are the radius of this particular curved flight path. Okay, similar like this one down here. So this radius is also important in our analysis for this performance. Okay, under this condition, the altitude of the airplane will remain constant. Okay, then the previous this particular question applies only to the case of level turn. Indeed, it is necessary condition for a level turn. Okay, so from what we have learned before, force or W is actually L cosine phi is this component going up, and L sine of phi is actually this one, Fr. Okay. So the generalized force diagram for an airplane in climbing and banking flight is given in the previous figure. Not this one, not this one. This is figure 6.1. Okay. When this figure is specialized for level flight, that is theta equal to 0, assuming thrust vector parallel to the free stream direction. This is actually the figure when we discuss about the what do you call it? When we want to derive the equation of motion for the aircraft, if you can still remember. Okay, so then the force diagram for a level turn is obtained as in this particular figure. Okay, the governing equation of motion, okay, like we have derived before. So you can actually obtain this particular expression, okay, equation 6.2, by assuming that theta is equal to 0 and this particular angle is equal to 0. You need to refer to this particular figure. You need to refer to the previous notes. It is there. So you have this particular equation. And from here, basically R2 is nothing but R2 is the local radius of curvature of the flight path in the horizontal plane. So in this case, you can replace R2 with R. Okay. So this equation is simply a physical statement that the centrifugal force, it is the centrifugal force, or this one, centrifugal force, is balanced by the force L sine of psi or phi. The two performance characteristics of greatest importance in turning flight are the radius R and the omega, which is the turn rate. Or we can call it simply the local angular velocity of the airplane along the curved flight path. Okay, then down here, if you can see, there is another equation, which is equation 6.4. So in this particular equation, what we want is actually we want to see the relation from what we have from here. L cosine of phi is equal to W. Therefore, cosine of phi is equal to W over L. Okay. So this is what we have. And if we rearrange this, we can see that the ratio L over W, okay, we swap this, or we move W to the down here. It is an important parameter in turning performance. It is defined as the load factor. Okay, load factor. Load factor will tell you basically how much forces that is acting on that particular aircraft at that particular moment lah. Okay, and for an aircraft there is a positive limit of load factor as well as the negative limit of load factor. Okay, negative limit means for example, if the aircraft is flying upside down like the aerobatic flight or for the fighter aircraft. Okay, not for typically not for commercial aircraft. If you do that, then yeah, that's probably the last day for the pilot. Okay, it is very uncommon lah for commercial aircraft, but for fighter jet, for acrobatic aircraft, then the negative load factor is very important. Okay, and this is the things, the relation. Okay, load factor is equal to L over W. Okay, this is another derivation to obtain an expression for the turn radius. Okay, this is a process for you to basically determine what is the radius. This one, R, okay, or this one. Same thing. This is from the front view and this is from the top view. Okay, this is the process lah. And finally, if you work on the you follow this process, I'm not going through this one. I hope you can have a look on your own later on to obtain this particular turn radius expression. Okay, so the turn radius is basically depend on the, of course, depend on the gravity, 9.81. Okay, but this particular gravity value is we can say it is constant in our analysis, but for this V free stream, it is very important because it is square, so the effect is very significant. And also down here we have a N, or the load factor. So there are if you exclude the gravity, you have two parameters that really important to determine your radius of turning. Okay, so from there you can also look into the on how to get the expression for the angular velocity, the speed at which you can turn. Okay, so the it is actually given down here. So the radial, the angular velocity for that particular aircraft, it is also depends on the load factor and the speed of the aircraft. Okay, so this is the equation for that. Then from this particular equation, we can see that the highest possible, okay, to obtain the largest possible turn rate, okay, if you want to, the aircraft is turning very fast, so you need to have the highest possible load factor, but you need the lowest possible velocity. Okay. And this is another process for you to determine the maximum possible load factor. Okay, this is very important. You need to know on how to determine the maximum load factor. So this is a process to obtain the maximum load factor. I'm not going through the derivation. I hope you can do it on your own, because it is not really difficult for me. I think you can do it on your own, right? Okay, try to work on this derivation. I think I will ask you to do this derivation later. Okay, so if you do the derivation, you will end up with this particular quite a long expression, equation 6.18. Okay, in this particular expression, you see the load factor. To obtain the maximum load factor, basically you need to also consider the density, or you can say it's depend on the altitude. Okay, because density is depend on the altitude. The higher you go, the lower the value of this particular density. Okay, and then the speed of the aircraft, V free stream, speed of the aircraft, and K down here is basically the coefficient, this one, for your induced drag. And W over S is nothing but that is your wing loading, W over S. And T over W, this is your thrust to weight ratio. So to obtain the maximum load factor, thrust to weight ratio must be maximum. And also your CD naught. Okay. So there are a few elements that you need to consider to achieve the maximum possible value of load factor. Okay. Okay, let's look into this another video.
As stated in Newton's first law of motion, an aeroplane's natural tendency is to fly in a straight line. If the pilot wants to turn the aeroplane, a horizontal force towards the centre of the turn must be generated. To keep the aeroplane turning, this horizontal force must continually act on the aeroplane's body. This force is called centripetal force. But as there are no fancy magnets in the sky, the aeroplane must generate its own centripetal force, and this is how it works. In straight and level flight, the lift force generated by the wings acts perpendicular to the relative airflow and opposite to the weight force. When the aeroplane banks to the side, the lift force tilts to the side with the aeroplane. The lift force can now be broken down into two components: the vertical lift component that opposes weight, and the horizontal lift component that pulls the aeroplane into the turn. The horizontal component of the lift force is the aeroplane's centripetal force. But what about the vertical lift component?
Okay, if you can see here, the vertical lift component is, if we look into this diagram, we can say that this circle is actually to show the magnitude of this particular arrow. Okay, the length of this particular arrow determine the magnitude. Okay, and if you compare this purple color for the weight, and if you compare with this one, the vertical lift component, the arrow is shorter compared to this arrow for the weight, and therefore you can see that the vertical lift component is not enough in this case to sustain the weight of the aircraft. And let's see what's going on next.
It's much smaller now when compared to weight. The aeroplane will begin to descend if the vertical lift component is not increased. The most practical way of increasing the vertical lift component is to increase the lift force. The pilot can achieve this by pulling back on the control column to increase the aeroplane's angle of attack. When turning, the aeroplane's load factor and stall speed increase. This is important to the pilot, and you can learn more about it in the next video.
Okay, so you can see by now, by increasing this part, the force, the lift force, probably how you can achieve this, you can use your flap, to basically improve your lift forces on this particular aircraft. Okay, here we have a figure 6.2. This figure is about the thrust and the CL max. Okay, constraint on maximum load factor and maximum bank angle versus flight velocity. So here we can see this particular aircraft having a thrust to weight ratio of 0.3795, wing loading of 76.84 pound foot square, and the CD naught is 0.015, and the value of K here is 0.08, and the CL max is 1.2. And it is at the standard sea level condition. So from this particular graph, on this vertical y-axis on the left, we have the maximum load factor, N, and on the right hand side we have the maximum bank angle. So this particular graph tell you not only one thing but two items at the same time. And down here, this is the free stream velocity unit in feet per second. So if you look to this particular graph, we have from equation 6.23, which we will discuss later, it will show you the stall limit, okay, and max for the stall limit, and also the thrust where it is constrained, and the CL max is constrained. Okay, you will see this particular this one is not F max. It is the angle phi max, PHI or PHI, I think. Okay, this one. Where was it? This one, phi. Okay, this. It is not F, so you need to change this. Okay, the variation of N max versus velocity for a given airplane as calculated from the previous equation. Okay, this particular equation shows is shown here, equation 6.18. The airplane considered here is the Gulfstream aircraft, like the one that we have seen many times in the previous example. And here we consider the altitude at sea level. The result will be difficult for different altitude. So we just focusing at the sea level. At the maximum velocity of the airplane, there is no excess power, hence no level turn is possible. So N equal to 1. As the V free stream, the speed of the aircraft decreases, the load, the maximum load factor is increases, reaches a local maximum value at point B. This one. Okay, and then decreases again. For velocities higher than at point B, okay, velocity higher than at point B. If you can see down here, point B is here. So if you increase, for velocities lower than point B, so point B is here. So anything below this, the drag due to lift dominates. Okay, it's more lah basically. This is why the N max curve first increases. So that's why it is it's going up in the first part, then reach a local maximum and finally decrease with velocity. So that's why it's going up and come down. Okay. At point B, the airplane is flying at its maximum lift to drag ratio. This is what we have. Okay. It is easily seen from the relation, recalling that the thrust is equal to the drag. Okay, that relation lah. So from there you can obtain this particular expression 6.19. So from that part, further expand, and finally you can arrive for when N max is constrained by CL max, the value of load factor, the maximum load factor, can be obtained as follows. So this is your N max. Okay. Okay, and another part that we would like to see is that the derivation for the V stall that is when you have to deal with the load factor n, like this one. How to get this one is basically what you have learned before. N is equal to W over, sorry, L over W. Where was it just now? Okay, this one, right? N is equal to L over W. So from here, if you move W to the left, what you will get is L is equal to NW or WN, the same thing. So this is what we can see here. Okay, L equal to NW. And from here, okay, lift is actually equal to half rho V square SCL. And we want to see the V. Okay, what is V? So rearrange this equation, then you get this one. Okay, and let's say we want to see the V stall. Okay, for the V stall, it happened when the CL is equal to CL max. So you just replace this V free stream with V stall and CL with CL max. So this is the expression that you will get. Okay. So you can determine what is your V stall. And this one is just now we already know on how to determine the, we know how to determine the turning radius, right? R. But how to get the minimum turning radius? So you want basically to turn your aircraft quickly, okay? So the minimum turning radius, perhaps at this particular moment, you don't have enough space to do the turning flight, okay? Let's assume like that lah. That's a condition. Probably you have obstacle at the front, or there are big mountain that you want to avoid. So that could happen. So we want to know what is the minimum turning radius that you can actually obtain. So this is the procedure. Okay, this is the procedure. So from what you have before, it is kind of similar to the previous equation, 6.9. This one, similar to this one. Okay. Then from here, basically, since we want to know the minimum value of turning radius R, so you need to do the you need to differentiate okay, with respect to the free stream or Q free stream okay, your dynamic pressure, okay, Q free stream, this is your dynamic pressure. So and everything here is equal to 0, and therefore you will arrive to this long equation. And finally, you can obtain this condition, okay, where the speed at which the radius of turning is minimum. So this is the equation that you can get through this mathematical process. Okay. And this particular equation gives the value of V free stream, which correspond to the minimum turning radius. This velocity is denoted by like this. Okay. In turn, the load factor corresponding to this velocity is found by substituting this equation into equation 6.28. Okay, substitute into this particular equation, this one. Okay, Q free stream equal to this, right? So Q free stream here and this one, you replace by this. Then you do the math, and finally you arrive with this. It is the load factor corresponding to the minimum turning radius. Okay, and finally, the expression for minimum turning radius is obtained like so. Okay, so this is three important parameter that you need to derive. Okay, this is examples where you need to calculate the minimum turning radius at sea level for the Gulfstream aircraft. Other parameter you can get from the previous example. Okay, so to cut short, okay, so from this equation 6.33, this is the equation. So you just basically replace all the values for these parameters. So K, you know, K is 0.08. The W over S or the wing loading is given 76.84. I think it is shown previously in this particular example. Right, this one. See, the thrust to weight ratio is given. Where was it just now? This one. Okay, the wing loading is 76.84. The thrust to weight ratio is given. CL max given. K is given, and CD naught is also given. So you can basically use all this information to solve work on this particular problem. Okay, and finally you get the minimum turning radius is 861 feet. Okay, and the corresponding load factor and velocity are obtained from equation like we have seen before. Okay, this one, this and this one. So just plug in all the values, you get the load factor is about 1.4. The speed is 165 feet per second. Okay. And finally, you can calculate your minimum turning radius with this particular formula. Of course, you need to calculate your CL. Okay. Now we want to move to the next part, which is maximum turn rate. Maximum turn rate. Just a second. I think. Okay, I just want to share with you one of our lecturers from our faculty. He is actually from the Department of Civil Engineering, Professor Associate Professor of Dr. Hussein, passed away around 1 o'clock today, this afternoon. I think, yeah. Can we recite Al-Fatiha for him? Okay. Okay, Associate Professor Dr. Hussein Ahmad. Probably you know him, I'm not sure. Or probably you have worked with him. So he is not with us anymore. Okay. 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 Let's proceed. For the maximum turn rate, the process given for maximum turn rate parallels that given above for minimum turn radius. Only details are different. Okay, I get it. Okay, this one is actually the process is similar to what you do here. Okay, the same process up until here. The same process. If you do that, you can arrive with this particular equation lah. Okay, so the derivation is not given. I hope you can do it on your own lah. Okay. So this is another example where we need to calculate the maximum turning rate and the corresponding load factor and velocity for this particular aircraft at sea level, Gulfstream aircraft. I think I've been flying with this Gulfstream aircraft last in 2015 with some of the students for flight lab at the Liverpool airport. I think that is the aircraft. It is a 14-seater aircraft. Very nice aircraft. Okay, if I'm not mistaken lah, if that is the aircraft. Okay, to solve this particular problem, first you need to calculate the your omega max or the radial velocity or angular velocity, okay, of that particular aircraft from this particular equation. Okay, all parameters is given, all the values for each of this is given, so you just plug in and finally you get this 0.25 radian per second, and you need to convert everything into if you want to solve in degrees, be careful if you want to solve in degrees, so you need to do this particular conversion. So omega max is equal to 14.3 degree per second. Okay, so the corresponding value of load factor is determined from the previous equation 6.35, where the the maximum load factor is calculated 3.16. This is the value for the load factor. And the corresponding value of the free stream velocity, you can calculate, and it is given as 3.86 feet per second. And finally, you can obtain the maximum angular velocity, where it is equal to 14.3 degree per second. Okay, for me, during exams, I prefer if you can give me in the unit of radian per second. No need to convert into degree per second. No need. You just give the value in radian per second. I'm afraid that you might have a problem to do this conversion. Okay, note that. Just give the value in the radian per second, like this one. This is also the same, the same value. Okay, let's look into this one.
When a pilot rotates the control column to the left, the deflected aileron column to the left. When a pilot rotates the control column to the left, the deflected ailerons effectively change the shape of the aerofoil. The left aileron deflects up, decreasing lift on the left wing, and the right aileron deflects down.
Okay, in this particular videos, it is actually explain what we call it adverse yaw. When you use your aileron, this is your aileron on the left, and this is another aileron on the right. As you know, aileron one going up, one is going down, right? To provide the rolling motion. So when this happen, of course the aircraft will roll, and at the same time the aircraft tend to have what we call it yawing motion at the same time. That's because of the pressure difference on this on the left and right wing. Okay, let's see what's going on.
Increasing lift on the right wing. As we know, any increase in lift is accompanied with an increase in induced drag. So the right aileron experiences more drag than the left aileron, and this results in a yaw in the direction opposite to the roll. This yaw is known as adverse aileron yaw. To prevent this adverse aileron yaw, the pilot must apply appropriate rudder in the same direction as the roll. A properly coordinated entry into a turn should involve only roll, and any yaw should be prevented by the pilot through use of the rudder. The adverse aileron yaw is a result of uneven drag being generated by the ailerons. Aircraft designers often incorporate features that help to even out the aileron drag and reduce adverse aileron yaw. Two of these features are differential ailerons and freeze ailerons. Differential ailerons are an arrangement where the downgoing aileron deflects a smaller amount than the upgoing aileron. With a larger deflection on the upgoing aileron, it generates additional form drag, helping to even out the total drag created by both ailerons.
Okay, what I mean from this, you see, the up aileron and the down aileron here, if you can see the displacement is different, right? It's going up more compared to the other one. So what happened is that, of course, we want to change the lift forces on this left and right wing, but at the same time, we want to maintain the same amount of drag created on this particular wing. There are two wings, right, on the left and right. So we want to maintain the same amount of drag. Okay. Why this one is going down less compared to this part here? Because as we know, for a wing, the shapes is an airfoil shapes, and the top on the upper surface of the airfoil, the curvature is bigger, okay, compared to the lower part of the airfoil. It's normally a flat, right? Okay, just imagine the airfoil, the top part of the airfoil is a little bit thicker, okay, or the curvature is a bit longer lah. And it basically changes the airflow on the top of the wing. Okay, that is the main reason lah.
With the drag generated by both ailerons being closer to even, the adverse aileron yaw is reduced. Freeze ailerons are designed with a wedge that protrudes into the airflow only on the side that requires additional drag. The aileron is hinged at the top and has a wedge at the bottom, such that the wedge is up inside the wing on the downward deflected aileron, but the wedge protrudes into the airflow on the upward deflected aileron, creating additional drag. Some aircraft incorporate both of these design features, so they will have freeze ailerons that have differential deflection.
So that's why there are two methods, right? Freeze aileron and the other one, where basically the main objective is to maintain the same amount of drag on the left and right wing. Otherwise, the aircraft is not only rolling, but it will suffer from adverse yaw. We don't want yaw during rolling. If we want to roll the aircraft, we just want to roll the aircraft. We don't want the aircraft moving to the left or right. So that is the purpose of this mechanism, why it is designed like that. Okay, this one is a pull up and pull down maneuvers. I think I will spare this for the next class. Okay, so we stop here. Screen sharing as Windows close. Okay, so we were here just now, right? So we stop at this slide number 19. So next class we will start from slide number 19 lah. Okay, on the pull up and pull down maneuvers. For today, we just cover the level turn flight. Okay. Stop share. And I know there are a few groups that need to do the presentation. Am I right? 2 or 3 groups. I can't remember. Shan?
3 groups actually, Doctor. If I
3.
remember correctly.
3 groups. Huh?
Yes, Doctor.
Can we do the presentation on the next class on Wednesday? Okay.
Yes, Doctor.
Okay.
Yes.
Because
Yes, Doctor.
okay, I have problem. I can't sit down more than 1 hour. I feel the pain. Okay. Okay, and I hope you already put the metric number, right? The metric number in the chat box. Okay, thank you for your doa in the chat. Okay, that's all for today. We only have class for about 1 hour. I'm really sorry. This is the maximum that I can go for today. Okay, I can't do more than this at this particular moment. Okay, thank you for your time. We meet again next class on Wednesday. Thank you very much. Okay, bye-bye.
Thank you,
Thank
Doctor.
you real soon,
Doctor.
Doctor.
Thank you, Doctor.
Thank you, Doctor.